Polynomials are easy functions to find the derivatives of and to integrate. They're just easy to work with. But there's other functions like sine of x that are not so easy to work with. It takes some special handling to figure out derivatives and things like that of sine of x and other transcendental functions. So we have this thing called a Taylor polynomial, which is a way that we can approximate a function using a polynomial. So what we're going to do is, if you did the exploration in the first part of this lesson, you saw that we can come up with a polynomial that is pretty good for sine, especially when it's close to the value of 0. What that means, centered at x equals 0, we can approximate a sine curve like this. So the sine curve is there in white, and that yellow curve is changing. You can see is this polynomial. So notice it starts off with a simple x, and then an x cubed, and then an x to the 5th, and then an x to the 7th, and the coefficients change. And you'll notice that at the beginning of this series there, so it's really accurate for at 0. It's always perfect at 0, 0. And then it gets a little closer. It starts to follow more and more of the curve, and that graphic stops. We could keep going, and we could get a better approximation. So there's a nice little picture of what's going on there. When we center a polynomial around 0, we call it a Maclaurin polynomial. It's a kind of a special form, but we could shift this, and we've seen in the past how we shift functions. We can shift it by just changing the x's to x minus c. This will shift the center, all right? So this in general is what we call a Taylor polynomial. So maybe we want it not to be perfect at 0, 0. Maybe we want it to be perfect at some other point, depending on the application. That's when we would use this Taylor polynomial version. So what's going on here? Well, by analyzing this function here, if we take the derivative, so this, by the way, this is called an nth degree Taylor polynomial. So it's nth degree because we're going to go to the nth degree and stop. So notice it doesn't keep going forever. So we'll take as many derivatives as we want until we get tired, and then we'll stop. Now notice this. When we take the derivative here of this, derivative with respect to x, then this constant goes away. And this, which has an x to the first, the derivative here will just be a1. This derivative, which has an x minus c squared there, when we take the derivative, we need the chain rule here and all that. But when we use the chain rule, the derivative of x minus c is just 1, right? So you don't see the derivative of the inside at all here. But the derivative of this would be 2a2 times x minus c. All right, and so on and so forth. So if we have this one, we drop it down, we'd have 6a3 times x minus c squared. That would be right here. All right, so all of these will still have an x, and we have an a1. All right, and then when we take the derivative of this next one, or derivative of this, so we're going for the second derivative. Well, this a1 goes away, and we'll have 2a2. Then if we take the derivative of this, okay, the constant goes away. Derivative of 2a2 is 0. And then we have this one, which was 2 times 3 times a3. And this goes away because we're taking the derivative of this. So on and so forth, all right? And what will happen is, notice, each of these are growing. So this coefficient was 2a2, and then when we took the derivative, it was 2 times 3a3. So this is 2 times 3. Because this exponent is going down, it was 3, then it's 2. The 2 comes out in front. Now we have 2 times 3. Okay? And then we have 2 times 3, or really 1 times 2 times 3. So there's really 1 times in front of each of these. And the next one would be 1 times 2 times 3 times 4 times a to the fourth if we kept going. All right? So you'll notice that the coefficients are growing. Do you recognize this? So we have n times n minus 1 times n minus 2. Okay? By the time we take all the derivatives down here, it'll be the factorial. This is 4 factorial, 3 factorial, 2 factorial. All right? So the definition of a Taylor polynomial comes out to be this. For the derivative here, the nth derivative will be n factorial times a sub n. Actually, to be more precise, this would be the nth derivative of p sub n of c. Because if we put c in here, then all of these x minus c's become 0. And all of these terms would all become 0. And all that's left over is that constant term. Okay, so the nth derivative of p sub n evaluated at c is n factorial of a sub n. So if I want to find a sub n, all I need to do is divide by n factorial. And now this tells us how we can find each of the terms. So this tells us a sub n is equal to p and n derivative evaluated at c all over n factorial. All right, so what does that mean for us? That means this. If I want to find any of these coefficients, which I do, so I can write this polynomial, I need to find a sub 0, a sub 1. That's all I need to find. And then I got my polynomial. All I need to do to find any coefficient there is I can take the nth derivative of the polynomial evaluated at c divided by n factorial. Well, how do we do that? We don't know p sub n there. We don't know the Taylor polynomial. That's what we're trying to find. Well, that's where the key comes in here, the key connection, and that is that since the derivatives must agree, the nth derivative of the function, like sine or whatever we're trying to approximate, has to be equal at c. All right, so the derivative at c for the Taylor polynomial is the same as the derivative of f, the function. So in order to find each of the coefficients, we'll take the derivative and we'll divide by the factorial. If we take the second derivative for a2 to find the divided by 2 factorial, to find a2, we'll take the third derivative divided by 3 factorial to find a sub 3, so on and so forth. And in general, we have this. Our general term is the nth derivative of our function evaluated at c divided by n factorial. And then we can build our Taylor polynomial. And we can get as accurate as we need. Okay? So, if f has n derivatives at c, then the polynomial can be, the polynomial here is called the nth Taylor polynomial for f at c. That means it's perfect at c, and then it's not as perfect beyond that. All right? If we're centered at 0, so if all these c's are 0, then this is called a Maclaurin polynomial for f. All right? So a little easier to deal with when it's just 0. So let's try this out for e. Let's find the Maclaurin polynomial for e to the x. All right? So let's start by finding our derivatives. So f of x is e to the x. F prime of x is e to the x. F double prime is e to the x, and e to the x. So e is the easiest function to take the derivative of because it always comes right back. Well, what is e to the 0? Well, e to the 0 is 1. What is, when we plug in 0 here, it's 1 and 1 and 1. Wow. All right, so what does this mean for our Maclaurin polynomial here? So we can look at this one. So before we write it out, one thing to see here, notice we got these factorials here, and then there's no factorials over here. Well, there actually is, and so let's continue the pattern. There's really 1 factorial and 0 factorial. But 1 factorial is 0, and 0 factorial is 1. And that's the same up here, all right? So every single term is going to be the nth derivative divided by the n factorial. All right, so keeping that in mind there. So you can notice the nice neat pattern. So here's our polynomial. This is our polynomial approximation for e to the x. So we have f of 0, 1, divided by 0 factorial. Now I'm going to go ahead and just write it out. So we have f of 0 over 0 factorial to start. And then the first derivative, which is 1, over the first factorial times x to the first. Then we have the second derivative, which happens to be 1, over 2 factorial times x to the second. And then we have the third factorial, which happens to be 1 again. That's just special for e to the x here, over 3 factorial x cubed, dot, dot, dot. All right? Then we can clean this up. So this is 1 over 1. That's 1. This is also 1 over 1, because 0 factorial is 1, 1 factorial is 1, so this is 1x to the first. 2 factorial is 2 times 1, so this is 1/2 x squared. 3 factorial is 3 times 2 times 1, which is 6. So this is 1/6 x cubed, so on and so forth. Okay, and we can also write it, you'll see it like this, 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 4 factorial. Well, that'd be 4 times this, 24, plus dot, 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 plus x to the n over n factorial. And there is an approximation for e to the x centered at 0. Okay, so let's see what that looks like here real quick. So let's go look at some Desmos here. Try to keep that in view there. All right. Okay, so here we have p. This is the first degree, actually the 0 degree, I guess it would be, because this is x to the 0 Taylor polynomial. All right, for e. Now notice it matches. There's e to the x in red. It matches right at 1, at one spot. I'm sorry, when x is 0, y is 1. So it matches right at when x is 0. All right, well, let's start adding some terms here. So we have 1 plus x. Okay, so that matches a little bit better. If we zoom in here, then we can see, whoa, that's not what we wanted. If we zoom in here, we can see it's a little better fit. And then, all right, so if we go plus, let's go x squared divided by 2. Ooh, look at that fit. Okay, so that, now again, the red is the correct curve. The blue is the approximation. That's fitting pretty good for a little bit more. Let's go ahead and add another term. And so we have plus x cubed divided by 6. Whoops, get in the right spot. Let's get out of the power. Divided by 6, there it is. Okay, even better fit. So as we do more and more terms, and now it's gone. If we do more and more terms, then let's do one more. X to the fourth and divided by 24. Okay, so we're getting an even better fit. Now, once we get out of a certain range here, now this is a terrible fit when x is -3. I mean, that's not even close, or -2. Okay, but up until this point, like -1.5, that's pretty darn good. Okay, and so on and so forth. It's pretty good. And then up here it starts to separate. So, again, that gives us an approximation, and the more terms we have, the better the approximation there.